Hey everyone, today I want to talk about another problem that involves dropping a ball with some air resistance. So in this situation we have a ball falling just thanks to gravity, and it has a resistive force of CV, where C is a constant that depends on the solid's geometry and the properties of the fluid that's resisting it. But what's important is that it's directly proportional to the object's velocity, so the faster this moves, the more it gets resisted until it's moving at a constant terminal velocity. So the goal of the problem is to find the ball's velocity as a function of time and its terminal velocity. So in order to do this, we're going to have to set up and solve a differential equation. So we can start just by writing the obvious, which is that sigma f equals ma. Right? And so I'll go ahead and have the mg be positive. So we'll say that mg minus cv equals ma. Now we can divide everything by m. G minus cv over m equals a, which I'm going to rewrite as dv over dt. Because ultimately we're going to want to solve this differential. Now, a little extra step is to make a little substitution that says that tau equals m over c, and I think this makes the differential a little easier to solve, so we can rewrite this as g minus 1 over tau times v equals dv over dt. Now, we refer to this as a linear ODE because we have, well, how about I'll just write it in an easier form to see. So I can write this as, instead of dv over dt, I'm going to write this as v prime, and then I'm going to move this term over to the right, plus 1 over tau times v equals g, right? And what you can see is that we have these v terms, right? Just multiplied by like some constant terms. And therefore they are linear, as opposed to like, I don't know, like a sine v appearing in the equation. Anyways. So, in order to solve this, we can use an integrating factor, which is equal to mu equals e to the integral of p dt, where p refers to this term behind the v. So we have e integral 1 over tau dt. It's going to be e 1 over tau t, which I'm just going to rewrite as t over tau. Okay, once we have our integrating factor, we multiply the entire differential equation by it. So we have e t over tau v prime is 1 over tau times v equals g e to the t over tau. Based on the chain rule, we can write this left side out as v e to the t over tau prime equals ge to the t over tau. And just to prove that we can write it out this way, right, I'll go ahead and use the chain rule to break it up. We can say ve to the t over tau prime equals, well, that's just v prime times e to the t over tau plus v times e to the t over tau prime, which equals v prime e to the t over tau plus v, and then you sort of have to like chain rule that. So that's e to the t over tau, then times the derivative of that, which is just 1 over tau, so that's over tau. So, right, and if we look here, we've shown that this here is equal to this statement here. In fact, just to make it super clear, I'll take the e to the t over tau out. Right, and now you can really see that these two statements are exactly equal to each other. This is a common technique in differential equations to find an integrating factor of mu, right? And then multiply both sides by mu, and then rewrite that like this so that we can separate and then solve this differential equation. But it never hurts to show why that works. Okay, so I'll delete that. So right, and as I said, this really, if instead of writing this as a prime here, you can write this as d of that over dt, which means now I can separate it out, which I'll go ahead and do that. Go ahead and write up here. So I can integrate both sides now. So this left side, of course, is just going to be VE to the T over tau, right? Plus a constant. We'll add the constant when I do this right side. So we're going to have to use U substitution for this integral. So we just say U equals T over tau du equals 1 over tau dt, therefore dt equals tau du. So if we go ahead and make that substitution, we can rewrite this integral as g times the integral, or g tau times the integral of e to the youth du, and that's just g tau e to the youth, which I'll go ahead and sub back in my t over tau, and plus our constant. So let's go ahead and rewrite this whole thing. So we get VE to the t over tau equals g times tau times e to the t over tau plus c. And what we can see here is we can divide by both sides. E to the t over tau. And now we get something like this. V as a function of time equals g times tau plus c over e to the t over tau. Now we need to solve for this generic constant c, right? And in order to do that, we have an initial condition for dropping, which is that the velocity is 0 at t equals 0, right? Because you're not adding an initial speed to the ball, you're just dropping it. So I'll go ahead and say that my initial velocity is 0 at t equals 0, so that's g tau plus c over, well, e to the 0th is just 1. Therefore, c equals negative g times tau. Perfect. So now I can make that substitution in and say that v as a function of time equals g tau minus g tau over e to the t over tau, which I can now rewrite again as g tau times 1 minus 1 over e to the t over tau. And there we go. There's my function for the velocity. Now the terminal velocity, right, would be the limit as t goes to infinity, right? What just speed will it approach? And we can see here that if this term approaches infinity, then 1 over infinity approaches 0. So this term sort of would like zero out, and then we would just be left with g tau times 1. So our terminal velocity is just g times tau. Now, if we just wanted the terminal velocity, that's not like the most efficient way to solve it, like solve out the entire differential equation. You know, you can solve that just with basic information. But anyways, it's a good thing to show nonetheless. So I'll go ahead and box my two answers. And there we go. Problem solved. Thanks for watching. Quick edit. In the video I said that you could solve for the terminal without having to do all this work with like an easier method, just using the basic setup. So I might as well go into exactly how to do that as opposed to leaving that super ambiguous. So the idea here would be that your dv over dt, your acceleration, would just be 0, right? Because that's when you're moving at a constant velocity. So you would want to know when 0 equals g minus cv over m, then, right, negative g equals negative c over m times v, or m over c times g equals v terminal. And then we said that m over c is what tau equals, so tau g equals v terminal. Anyways, there we go. Now with that, thanks for watching.